So that represents my point of observation. Consequently, my point of observation is related to position vector associated with our origin. This will be our x, y, z coordinate system. And finally, the relative position vector pointing from the central position of our source, current source, to our point of observation is r. We now have the ability to determine the magnetic vector potential at any point in space because we know what m's pointing. We know what that relative position vector is. And the remaining components are either units associated with the type of system that we're using, unit system that we're using. Of course, we're using MKS system. And that will be divided by the distance, relative distance cubed. And n is known. So consequently, we see that we have really a very general expression at this particular point. For a current source in the z is equal to 0 plane with central location at the origin last lecture we calculated the magnetic field, magnetic flux density by making use of the curl and evaluating the curl about our point of observation. And remember, this is a point form law. You see, it says nothing about where the source is. And it's not a source at a force at a distance law. It's about a small region in space. Well, making use of our cross product, we demonstrated last lecture that our magnetic vector potential will give contribution will give rise to a magnetic flux density, which is of the following form. It's equal to mu naught times the magnitude of our magnetic dipole moment, m, and as mentioned last lecture, we could have also expressed it in terms of the differential of m. It just depends on relative size. It's not going to depend on much else. Divided by 4 pi times the radius from the origin, or if you like, the distance from the central location of our source to our point of observation, squared, cubed, times the quantity 2 times the cosine of theta sub p plus the sine. And that's in the radial direction, which is a function of theta sub p and phi sub p, plus the sine of theta sub p times the theta unit vector, which is a function of position of our point of observation.
Did you use point form because of, since we're looking at a current source in a whole plane, so a whole region, instead of just at a point, that makes it, so we use the point form?
We use the point form because A is valid in our entire region. We only have the one source that's present, and the only time that A gives us a problem is when we are standing at the source, because then R goes to 0, and then you get a 1/0 condition. So excluding that particular point, this is nice and uniform over all space. Since it's uniform over all space, I can take its derivative or curl or whatever operation. So we covered that last lecture for the magnetic dipole moment. We also stated for the magnetic dipole moment is that it can generate a torque in our system. And that's very important. And we showed last lecture, and that's going to be needed for today's lecture, that the magnetic dipole moment, when it feels an external field, it gets torqued in such a fashion that the magnetic dipole moment points in the same direction as the external field. So we'll say for orbital motion, of our current,